Welcome to Rust Belt Science. I'm your host, Maggie Fink.
And I'm Shahir Risk.
And today we have with us Adam Jaffee, who is an assistant professor in the chemistry and biochemistry department here at the University of Notre Dame. So welcome.
Thank you. Thanks for having me.
Of course. We start off every episode asking our guests a non-science or research question. Is there anything you are reading, watching, or listening to right now that you'd like to share?
Let's see. Watching right now, this is just maybe coincidental from getting to the Midwest, but my wife and I enjoy watching Formula One racing.
Ooh.
And so we're, there's a Grand Prix this weekend, and this is the third in a triple header, so I'm going to watch that this weekend. Reading, I'm off and on, but I've really enjoyed a book. What's it called? Blanking. Yeah. It's all about how animals perceive the world. And so.
Is that the Ed Young book?
Yes.
It's an immense world.
An immense world. Yeah.
World,
No, I was blanking on that, but really enjoying that. And, all the different kind of the more familiar senses, but also some of the more unfamiliar ones. So.
Wonderful. So an Ed Young.
Yeah, that's a great book. Highly recommend.
Yeah. And things like echolocation, electrolocation. Yeah.
Yeah. The Grand Prix that's happening, where is that taking place?
That's taking place in Saudi Arabia.
Yeah.
And so I don't know the exact time difference, but it actually works out pretty well to watch it kind of in the middle of the day here.
Yes, because they're ahead of us.
Yeah.
So at night there is during the day
exactly,
here.
Exactly.
Yeah.
And so, yep. A big Lewis Hamilton fan. He made a big change to Ferrari this year. So it's been fun watching him in red.
Wow.
I mean, I'm from Indiana, and I've never watched a car race. I've never been to Indy 500, nothing.
Disc.
I know it's a big thing. In the Midwest, it's kind of lots of that going on, but I've never. So, but I've heard a lot about Formula One racing lately. It seems like it's kind of in the zeitgeist a bit.
Yeah, there's a Netflix show that came. It's now in its like sixth or seventh season called Drive to Survive, and I think that got a lot of people into it. I had never watched anything previously either, but I was pleasantly surprised that it's not only going around in an oval sometimes. So
yes, they have different. They have like S curves and so on. And I've watched a little bit of it, not a whole lot, but sometimes I've enjoyed watching when they have it at night. The races at night, and you can see when they hit the brakes how the brake pads going against the rotors will just burn bright.
It's pretty impressive.
From the friction. It's amazing.
Yeah. And that really, I think, speaks to some of the cool, and this is the nerd in me, the cool science, the engineering behind it, right? Yeah. Because, I mean, the sheer stresses that those materials have to take are pretty impressive. And so I think that's one of the reasons I like it so much. I like just watching sports, but, you're also, you see some really top of the line, cutting edge engineering and kind of science behind it, of both aerodynamics, but materials design. So it's pretty neat.
Yeah, and they're all limited to a fairly small engine, is my understanding, right?
And that's starting to get to the boundaries of my understanding. But I've never been like a car person, knowing too much about it. But they're not. I think they're maybe even V6 engines,
It's pretty basic stuff that you would find like on a Buick. Obviously not, but
right.
capacity-wise, these are not like
exactly,
huge, So then they have to do all this other stuff just to make a reasonably small engine go. Like, I don't know, how fast do they usually go?
Oh, I mean, they're upwards of 200 miles an hour.
Yeah. That's just insane.
Frightening to me.
It's wild. Yeah.
It is super cool to watch, and there's so much drama that takes place. I imagine.
Oh,
like
for sure. Yeah. It's like 20 of the most egotistical people racing against each other and kind of competing. So it's always going to be some fun drama there.
Yeah.
And apparently they have some of the best reflexes of all sports.
Yes.
Of all athletes, right?
Yeah. Amazing reflexes. You watch some of the more kind of theatrically intense ones. You'll even see pre-game, like kind of sticking both their hands out and waiting to catch tennis balls that their trainer is dropping, like to have that quick of reflexes.
Yes, at either hand, they don't know which one it's coming from.
Exactly.
Yeah.
And they also have really strong necks because the sheer G forces that you're sustaining are huge going around those curves.
I hadn't thought about all those things that go into them. Like, it's just cars, which are not super interesting to me. But,
I know. Yeah. It's
but
wild.
I guess they are athletes in that sense.
Yeah.
So
and cars are fascinating machines. Okay. I really enjoy cars. I really like cars. So From that, I mean, obviously there's the drama of the sports, watching it, but also there's the technology part, and that kind of touches a little bit on what you do with materials. Yeah. So you're a material scientist in a sense. Is that correct?
I think that's accurate to say.
That's accurate to say. And I watched you give a talk, and the title of the talk had something called hybrid bronzes in it.
That's right.
And when I think of a bronze, I think of like a bronze statue. Right?
Sure.
Because, I'm a biochemist. What do I know about like metals other than like, here's some zinc that you need to take for some enzyme.
Right.
And so for me, a bronze is something that is like an alloy of a bunch of different metals, and it has this nice color, and you can make statues out of it.
Absolutely.
But it means something different for you in your field.
Yeah.
Can you tell us what these hybrid bronzes are, and tell us a little bit about what you're using them for in your research?
Sure thing. Yeah. So you've hit a lot of points dead on about what bronzes are. So and a lot of people also know it from like Bronze Age. It was really important for human development. It's a copper tin alloy, and it's shiny. And so that name bronze was then taken and used by it's actually not clear who first used this for an entirely different class of compounds, but these are metal oxides, so metal bound together with oxygen. They make a whole range of different kind of structured compounds. Like if you were to look at the atomic level, the atoms are arranged in different ways, but what they share in common is that these metals have kind of variable or mixed levels of electron density, of electrons. And having that mixed valence, as it's called, allows electrons to really move around freely in these compounds, much like they do in metals. I think we're all familiar with like metals being really conductive. You use it for like electrical wires and that kind of thing. So electrons move really freely. Metals are also shiny because of these free electrons. Those electrons can oscillate when light hits the sample or hits the material, and so that reflects light and makes it shiny. And so people discovered like these metal oxide compounds, when they're mixed valence, some of them at least look shiny. And so somebody was like, ooh, a bronze. Yeah. And so that was back in the 1800s. German chemists, Friedrich Wöhler was often credited as calling them bronzes, but actually we've tried to look back and can't find in that original German paper any mention of the word bronze.
Oh, wow.
But soon after, somebody started calling them that. Yeah. So anyway, okay, so that's all the history lesson, but these bronzes are just really interesting materials because having those free electrons allows them to do a lot of really neat things. It allows them to absorb light, and so they're not only always shiny, sometimes you can change their color by how many electrons are in there. They are conductive, but you can even make them superconductive. And so that's, I don't know if you're, exactly. I don't know if you're familiar with superconductivity, but that's essentially conduction of electricity with zero resistance, meaning most things, even metals like copper and silver, there's some resistance to electrons moving through them, and that resistance causes them to heat up when electricity is moving through. But a superconductor would be really great because it allows electricity to move freely without any of that. So it's great for energy storage, energy transport, all that kind of thing. Okay, so there are all these great properties about bronzes. The hybrid bronze part comes in where my lab's story begins, and that's that we are materials chemists who really like combining the benefits of molecular chemistry. And so a lot of us, I think, are familiar with molecules, like anything as simple as the air we breathe, which is made up of oxygen, O2, and nitrogen, N2, water, H2O, ibuprofen, whatever it is. Those are small molecules, and chemists are really good at designing molecules to do exactly what they want, like adding or subtracting atoms. Yeah. So we like the idea of being able to do that, but in a solid state material, something that like you could make a battery out of, or a solar cell, or an LED. And it has all of those conductivity properties and the wonderful things that the bronze has. And so can't we put the two together? And so that's where hybrid bronzes came from.
That's fantastic.
That was a pretty long answer. Sorry.
That's a great answer. So this idea of superconductivity, I think it really intrigues me. We use copper wire. Yeah. And, copper is like kind of one of the best materials. And that's because, like you said, it has little resistance. Right. So that you put current through a copper wire, eventually it'll heat up. Yeah. But not as much as, like, let's say some other material like iron or something, lead. Or lead. Yeah. It will still conduct electricity, But you're saying a lot of that energy will go into heat rather than actually completing the circuit. And so copper is really conductive. But then what makes a material superconductive, and why don't we have that in like our phones or in our walls, I guess?
Yeah. Oh boy, that's a really deep question. So in general, there are multiple ways that materials can superconduct, and I'm certainly not the biggest expert on this, although I have some sort of forays into the field, just or at least knowledge of the field as a function of my group also looks at the properties of things under really high pressure. And I don't know if anyone's followed, like recently, there have been some kind of almost controversial things going on in superconductivity recently, like this even made it to the mainstream of like LK99 and some other compounds developed. Almost all of the superconductivity developments recently are conducted under very high pressure. And what you're doing there is you're literally squeezing atoms closer together. That allows their what are called orbitals, where the electrons like to exist, to overlap better. And so those electrons can essentially move more freely and interact with each other. And that can lead to that superconductivity. So in superconductivity, the difference is that electrons can interact with each other over much longer distances. They're coupled to each other almost. So, if you have electrons that are coupled to each other, they're going to be less likely to scatter or bounce off of impurities or defects or even vibrations in a material. And those are the things that lead to that resistance in just simple metals like copper or really any other material. So it's really allowing the electrons to almost like skirt around or sort of like pass through these defects without interacting with them, and therefore that electricity can be conducted without any resistance.
So that pressure is basically just pushing everything together. And what kind of pressure are we talking about here? Is this like, my hands kind of squeezing it together? I'm guessing it's much higher than that.
Funnily enough, we achieve it just by turning a little Allen key in our devices that we use, which are called diamond anvil cells. It's a really simple device, actually. So pressure is force per unit area, as maybe some of us remember. And so what that means is either you can try to apply a lot of force, or you can just make your area that you're applying that pressure over, or that force over, very small.
Very small.
So we take these two diamonds that have really, really tiny tips, maybe like 300 microns across. And that's what we're squeezing our samples between. But yeah, we get to what are called gigapascal scale pressures. And for reference, 1 atmosphere where we're living and breathing right now, that's 10 to the 5 pascals. So there's 100,000 pascals. And so 10 gigapascals, that's like 4 orders of magnitude higher pressure.
Right, so like 1,000 times more than what we would see at sea level.
10,000.
10,000. 10,000 times.
Yeah.
I can't count.
And for reference, let's see. I think the center of the Earth is about 330 gigapascals.
Wow.
Center of Mars, I forget. It's somewhere between like 40 and 60, maybe. Yeah.
This is really difficult to kind of imagine and wrap your head around things happening like at the electron level, and then also these massive, pressure numbers. And we've had some astrophysicists and astrobiologists on here talking about like massive things, and that's really difficult to comprehend on that scale. Now we're zooming back in,
right?
And it's interesting as somebody who studies biology, these things that aren't really living, outer space and electrons. I mean, I guess you could argue they're essential for life, but I'm curious how you view them, because we kind of talk about them as if you're personifying them in some way. And maybe this even could lead into a question of how you got interested in this type of chemistry. For a lot of people, it kind of seems maybe stale, right? It's almost more in the mathematical world. I'm kind of rambling with the question. I don't know if it's making sense, but
no, I think so.
How do you view these things that aren't really living, even though you're kind of treating them like they are alive and you're changing how they behave, and why you got into this kind of work?
Oh yeah, such a good question, and there's probably no easy answer. And I also love thinking about the living world, and like the everything from microbes all the way to elephants and bigger. Let's see. So I think just the really simple answer of why I got into chemistry and why I was so interested in it is both, some personal stuff that I'd be happy to get into, but also I love pretty colors, and I love fire, and I love unexplained behavior, like, why do magnets attract each other, and, all these cool phenomena that then later on, when I started to learn more about it, you also realize, this actually also relates to really important things for humanity. Like, how do we store energy? How do we transmit energy? How do we have these giant screen TVs that we can view beautiful pictures and movies on? How do, all of this is so interconnected. And I think that's what really attracted to me, is both being able to kind of scratch that itch of solving puzzles and understanding what makes the world tick, but also, helping the humanity and its challenges.
That's wonderful.
Yeah, I think I initially went to school for biochemistry, but chemistry was really what I loved initially. And actually, I was very close to moving away from biochemistry and going into nanochemistry. I took a nanotechnology class as an undergrad and really loved it.
Oh, cool.
And thought that world was so interesting, that things start behaving differently when you get so small.
Right.
And again, it's really difficult to comprehend. And then I ended up, I don't know what happened, but I did not go into nanochemistry and things like that.
That's because bacteria control your brain.
Yeah. So what drew you back more towards the more biological side?
I think it was difficult for me to visualize the chemistry that was happening, and there was just something missing. And I liked it, and it wasn't that it was new at the time, but that was almost a while ago. And I just don't think there was quite the same amount of information. And I struggled to really see my place in it. And then, I started going more towards biology and proteins, because those were more visual and I could see it and move it around in my head. But the nanochemistry started to become really abstract, and I struggled to comprehend it.
Right.
So I was content with just kind of understanding things behave differently at the nano level, and that was wild. And so now I just tangentially am interested in it. But it is a difficult concept to grasp, I feel like, that things no longer obey the laws of physics.
Or at least the ones we're familiar with. Right. Yeah, no, I completely agree. And still, like, I'm sometimes very, like, blown away by counterintuitive phenomena that is, like, just because we are existing every day in life under kind of very classical physics, it's very difficult to put your shoes in put yourself in the shoes of an electron again to anthropomorphize it, it's some very counterintuitive stuff. And so but I don't think we shouldn't be too hard on ourselves. Even much smarter folks than us, like I don't know, Einstein had trouble with quantum mechanics and all that. That's true. Not trouble with, but just like that, it also felt counterintuitive.
It did, yeah. So going back to that kind of idea, so what happens at these very, very high pressures? What do you guys see? How does that world behave, and how does it behave so differently from our world, which is kind of like, we imagine as the billiard balls. You bump into something and moves. What happens at those really, really high pressures at a very, very small scale?
Yeah, well, so I think the neat thing, and maybe this is getting back a little bit to your point about visualization and trying to understand how they evolve under pressure. Often, or at least more often than not, what we end up eventually seeing, though it's very difficult to get to this conclusion, is some pretty simple phenomena. So a lot of those, going back to those like metal oxides I was talking about, typically you'll have these metal centers surrounded by some number of oxygens. Usually it's like 5 or 6, maybe in something called an octahedron or maybe in a square pyramid. And in these extended solids, these metal oxide bronzes or other materials like that, you're essentially just chaining together all of these polyhedra into maybe layers or 3D networks. And so when you compress anything, that force, that energy you're putting into the system has to go somewhere. And so, physicists and chemists refer to this often as like PV work, pressure volume work. You're putting energy into the system. You can't violate thermodynamics. That energy has to go somewhere. Right. And so it usually has to either compress the bonds, the distances between the metals and the oxygen atoms, or you can even have these polyhedra tilt relative to each other. And so it's kind of fun because, you're just visualizing this as like tilting of shapes or maybe distortion or shrinking of the shapes. And so that actually gets down to some pretty fundamental, geometrical concepts. But then what I find really cool is so if those metal oxygen distances are shrinking, that means that their orbitals, again, where those electrons exist, start to overlap more. Or if you tilt the polyhedra, they start to overlap less. And so that can lead to changes of like how those electrons behave in the system. And that manifests in at what energy threshold do these samples begin to absorb light? So like once you get to some high enough energy, do they start to absorb light? And what that means is these samples change color. So, you know, sometimes you're going to start with something that's white or light yellow in color, which means that it's not really absorbing much in the visible spectrum.
It's reflecting most of it back.
Exactly. Yeah. Because just the
white light to white light.
Exactly. But then under pressure, maybe you'll all of a sudden see something go to a much darker red or black color. And that means it's now absorbing light in the visible at lower energies than it was before. And so that tells you something about how those polyhedra shifted around or were distorted. Yeah. So you get all kinds of cool changes like that, as you might imagine. Changing of that orbital overlap also changes conductivity. But if you have some of these molecules that we've tried to put into our compounds to have that additional synthetic control, those kind of can squish and distort and sometimes react. And so you go to all these different phases. And all of this might seem very like, okay, yeah, but like why? Like why would anyone care? But I think the really cool thing then is pressure is this like unique tool where you can then understand all of these essentially structure property relationships, right? And we're doing that systematically. We're systematically applying pressure and we see what happens. And then we can say, oh, okay, we got to something that absorbs light differently or emits light differently or is more conductive. That's a really desirable property. Now we can go back to the benchtop, design material 2.0 and do that chemically. So not need like those gigapascal scale pressures.
I see.
And so actually, okay, if you think about it, again, pressure is force per unit area, right? Well, a really, really, really small area is just the size of one atom. Atoms are tiny, right? And so if you imagine substituting an atom within your structure for something that's slightly larger or slightly smaller, you're effectively incorporating chemical pressure. You're changing, you know, this local strain that little atom is creating, but maybe even getting to similar behaviors that you got when you were squeezing your thing with diamonds.
So instead of squeezing it from an external pressure, you're just squeezing something in there, just stuffing something in the middle there.
Exactly.
To create the same effect. Or a similar effect.
Trying to. And of course, there's lots of complexity here, but that's kind of the gist.
That makes so much sense. Again, these things can be difficult to visualize and conceptualize. And you did a really good job explaining it to somebody who has not thought about this kind of stuff in a very long time. And again, I love the way you talk about behave and like force it to do something as if these things are, I don't know, it just
we need to do more of that.
And I
really
think
need to do more of that.
It really, I'm trying to think of what I want to say. That's kind of discouraged a scientist to talk about even living things, like as a microbiologist, talking about bacteria in that language of they're behaving this way or they want this thing, right? They don't have that. But then even talking about it in electrons, and I think it just makes the science so much more accessible, and it showcases the scientist's joy in doing what they're doing, because you have a relationship then with what you're doing, even if it can't have a relationship back with you in some way that we know of now. Maybe they do. So I really appreciate the way you talk about it, and it makes me happy, even though I, was stressed out when I took PChem back.
Sure. We all were. I think that's a really interesting point that you bring up, and like you say, like that more of like anthropomorphizing of inanimate objects, even like at the atomic level, is often discouraged. And I, of course, have to strike a balance when teaching about all of that, because electrons don't have feelings, and that kind of thing. But like you say, it can be this tool for helping with understanding, as long as we kind of continually acknowledge the fact that, like these are complicated phenomena occurring that are ultimately at the whim of just, universal kind of almost rules or whatever, like thermodynamics. But that, like to understand what's actually going on, sometimes it really helps to kind of simplify things a bit.
Yeah. So your work, you're trying to synthesize new materials, essentially. Which I guess kind of would fall under an engineering type of mindset. Would that be fair to say?
Yeah, I think so. I think there's a huge overlap between engineering and science, and absolutely.
Okay. So what will these materials that you're creating be used for? Like, what is their direct application? Obviously, talk about kind of energy broadly, but Where do we see these kinds of materials in our everyday lives?
Yeah, it's nice to get specific, right? Because you don't want to be too abstract. Yeah. So I think I mentioned some of these bronzes, you can change their color, right? Mm-hmm. And one wild fact that I heard recently is that something like 30% of all of the energy that humans produce goes to buildings. And that's combining everything from its, the actual construction of the building, but also a lot of it to its heating, cooling, and lighting. And if we had better ways to more efficiently heat, cool, or light buildings, that would be a huge energy savings. Yeah. And one kind of technology that could be really helpful with that is something called smart windows, otherwise known as electrochromic windows. Electrochromic meaning they change color when you apply potential. Mm-hmm. And so there are some fancy airplanes even that have these now, and a couple, maybe rear view mirrors and fancy cars, and a few things where you flick a switch and it goes from essentially transparent to dark. Or back again.
My airplane I was just on had something like that.
Yeah. A flight to Japan that I went on several years ago, they basically simulated a sunset with these windows. Cool. And then we all just magically fell asleep, even though we were following the sun the whole time going west.
We're so subject to our circadian rhythms, right?
Exactly. Yeah. I woke up and was like, oh, it's another day. But the sun had been there the whole time.
Yeah.
I was fascinated by the material, so I'm really glad that you're bringing this up.
Yeah, totally.
So keep going. This is great.
Well, and so everything's connected. So the most studied electrochromic material that's used in these smart windows is tungsten oxide, which is essentially these bronzes that the inorganic version, not the hybrid yet, not what we're working on, but it's a metal oxide bronze. When it's just WO3, W is the chemical symbol for tungsten, it's colorless. But then when you reduce it, when you give it electrons, it becomes dark blue. And so you just do that just like you would in the batteries that power our cell phones and all of that. All you're doing are these reversible reductions and oxidations, pumping in or pulling out electrons. And so you're doing the same thing into a window that just happens to be transparent and has this material in it that can accept or release those electrons. And so, that's what changes its color. But there are a lot of issues with these technologies. You want all technologies to always be long-lasting, non-toxic, inexpensive, to be able to switch quickly. So all of these things could do with some improvement. And so we think that the hybrid bronzes that we're working on can have a lot of the benefits that tungsten oxide and some similar compounds have. But maybe, first of all, we can synthesize our compounds under much, much milder conditions. Tungsten oxide, you typically would synthesize that at many hundreds of degrees Celsius for kind of a long time. And that takes a lot of energy. Right. Our compounds we can make by stirring some things together in water at just a little bit above room temperature. So that's pretty nice.
That's cool. Yeah.
And having all of those little tuning knobs, those chemical tuning knobs of different molecules we can put in, different metals we can put in, should allow us to change what color that these smart windows would go to, or how quickly they switch from colorless to not, or even ones that might have dual modes of operation. Like maybe you want to let through visible light in the winter when you want to brighten things up, and also let through IR light. So that's heat essentially. Infrared light. Yeah. But maybe in the summer, you still want to be able to see during the day. You want to let in visible light, but maybe you want to block out that heat, that IR light, that infrared light. And so maybe you have dual modes of operation where you can switch all of that around. And so that's one area. We also think that our compounds could be good catalysts to be used to essentially make it easier to synthesize other molecules, essentially assisting by joining together or breaking apart atoms. And a few other things, like maybe just as layers that you would incorporate in devices like transistors or LEDs that just allow you to better transport electrons, better transport charge. And so we see a lot of different avenues that we can take these things. And our goal was to start out by designing a material platform that just has a lot of these tuning knobs, a lot of different ways of, overall we know some of the criteria we need for so many of these technologies. And then now we can sort of get down to a little more of the engineering side of things and say, okay, well, if we want a good catalyst or we want a good LED, let's tune this knob or tune that knob. Yeah.
Well, that sounds cool. It sounds like cooking to some extent.
Very
because,
similar.
like you said, you just change the recipe a little bit and you get something a little bit different.
I haven't tasted them yet.
Yeah, probably not a good idea.
Yeah.
But I really love the idea of being able to have, instead of just light, dark, to have that high level of control of which type of light comes in. I think that's super high level, and it's super cool. That's really exciting.
Yeah, I have another question, and maybe this is not something that you can answer, but talking about making these materials for products, I don't think people understand, as researchers in an academic space, what that looks like as far as how do you, a scientist, a professor, then take that product into the real world. I think there's been a lot of chatter in the biomedical fields of things like drugs and things like that. It's kind of a hot topic, and people don't understand that process.
Right.
And I don't think people realize that happens not just in pharmaceutical arenas, but if you make a product in your lab that then a company will use or buy, what does that process look like? And maybe that's not something you've encountered or do. I don't know, but it sounds like it might be something that you have come up against.
That's such an interesting question. Yeah. And yeah, something that I think is still opaque to a lot of folks. So first, I think your comments about engineering were spot on, and that kind of relates to this. So I view so many of the sciences as being really interconnected, or like there's some huge Venn diagram with many, many different circles, and there's a lot of overlap everywhere. And the way that I view the science that we do is a little more on the fundamental side, which I think was maybe already came across in the, like, we're squeezing things with diamonds to understand at the atomic level what's going on. But, we do, of course, have an eye towards, like, how can we help humanity? How can we, make materials relevant for energy-related applications? And so it's kind of, the way I view it is this whole spectrum. Each part of the spectrum is super important, all the way from, like, those initial discoveries and fundamental understanding. And that's a little more where we sit, all the way to much more engineering aspect of things of, okay, we've got something that kind of sort of works, but let's really optimize it and make it really functional. Then we can take it to market. And so, I think our compounds have a lot of potential, I'd like to think, but we haven't yet taken them to something, that would be implementable in market. So we take it all the way from making these new compounds, doing a whole lot of characterization of figuring out what makes them tick. And maybe we'll even do some sort of test applications, like make a little battery or make a little smart window and just generally see how well it works. But, if these compounds were to eventually make it to market, our little test cell is sort of like the Mach 1, the material 0.0, like not even 1.0, and the development and improvement would probably, hopefully, be massive once we've sort of like established that initial platform. But it's. By the way, I should also, before going any further, say I'm hugely grateful and thankful to have, like, a wonderful lab of graduate and undergraduate students who are really the ones who are doing all of the work. And that's also maybe something that not everybody knows if they're not in academia, is that the primary scientific workforce in academics are graduate students, postdoctoral fellows or associates, and also undergraduate students. And they're the ones physically in the lab doing these experiments. And my job is to first, teach folks how to do this stuff, a lot of the more specialized techniques especially. But then I'll just provide a lot of kind of more higher level guidance. And, I talk with my students every day about, okay, what's next and how do we figure this out? But so they're making these discoveries, and then eventually, like if we come up with something that we think is working pretty well, we might then take it to try to maybe patent it, and that patent might then eventually get bought by a company who would be interested in developing the technology further, or sometimes academics do found their own companies and kind of develop a technology from there. So, but that's, to be honest, not something I have as much experience with, but I think I have that overall perspective of where we sit on that spectrum.
Yeah, and I think you make a good point. Across all scientific disciplines, basic science is where all discoveries start. There's lots of examples, again, in the more biological world of studying something like cone snails now has led to massive pharmaceutical treatments. But you didn't set out to study that specific thing. And I think...
That's so cool. Wait, what did people study in cone snails?
You Shahir knows it more. You can, I think it's in
well, there's basically, I mean, they were known to be toxic.
Like super toxic. Like dangerous, right? Yeah.
And they thought, okay, well, there's like one thing that kills you. Well, it turns out there's like many, many, many things that kill you in each venom in that cocktail. And in fact, each one kind of kills you in a different way. And they all interact with the nervous system a little bit differently. And so it was kind of an accident the way that they did this experiment where, I think it was a couple of undergraduates who basically just separated all the different components. And then this was a long time ago where you could easily do this. And they took each one of the components, so they did on something called HPLC, which you're familiar with, which is just a way to separate mixtures, the components of the mixture. They took each component and they injected it into a mouse. And then each mouse died in the most bizarre way.
Gruesome.
And some didn't die, but they just started twitching, or they would their left side of the body would, paralyze, or the right side, or they would just do the weirdest things. And so now a lot of these molecules are being tested or even approved for, as painkillers or as neuromodulators somehow. So
amazing.
It's a crazy story. And, things like that just happen when you're just curious.
Agreed.
Yeah. And there's a lot of examples in engineering, material science. I mean, like lasers. I don't think people realized the potential of what we do with lasers every day now when lasers were discovered.
Absolutely.
Came from play.
Yeah, which is where basic science starts off, is people just being curious. And it's not, at least in my experience, it's less and less valued if you don't have like an immediate, like this will be applicable to cure this disease. No, we're just kind of curious because it's an interesting thing.
Right.
And it sounds like that, like you said, that's where you sit more. It was this like, well, let's just try some stuff and see what comes of it so that we could better understand the chemistry.
Right.
As opposed to we're making engineering a specific product. It might happen.
Yeah.
But it's more just a space of curiosity about what you could possibly do.
Right.
Yeah.
Let's squeeze a bunch of atoms together.
Exactly. Yeah. No, but I think I kind of lament the fact that I think even the more industrially, companies used to value kind of more basic research a lot more too. So I
That's
think
true. Yeah.
A lot of folks are familiar with Bell Labs, right? This I guess eventually AT&T, Pac Bell, or whatever, but I don't know all the history of the exact change of hands of different companies, but this was like a company owned, so like for-profit institution, but that was funding all this basic research, and that's where the transistor got developed. That's where all of modern computing came from. Like that's also where a lot of early stuff related to lasers came from. And so, all this stuff.
Same with 3M as well. They had a huge, they might still do have a huge just research and development part where they just dedicate a lot of time to making things like Post-it notes.
Yeah, exactly. Right. Yeah, true.
Yeah, I feel like I fund the Post-it note industry with the amount of Post-it notes I have in my lab.
Buy stock.
Yeah, I do. I buy them at Costco. And
what do you use them for? Are the notes just for yourself, or are they for
everything?
All the things?
In our lab, it's like I am using this, and like sign your name and put it on a machine. So if people need it, they know your stuff is in there, or like
claiming it.
Yeah, I write like lines of poetry and put them on my lab bench as well that I like, just to keep it more.
Yeah.
So instead of a Google Calendar, you guys just have like a.
Sometimes my lab notebook I don't write it in my lab notebook. I write it on a Post-it and then just stick it in my lab notebook when I get which is very bad practice. You should not do that. But I'm not discovering anything. Hopefully my advisors know. I'll write it down. But sometimes you just need a Post-it note to just like, anyway, I love Post-it notes.
You're just exposing yourself
I'm
out.
sorry.
Well, Adam, you're asking really great questions. Maggie, if you ever are looking for a replacement for me.
Oh, my God.
Yeah. I'll just have Adam come be my new co-host.
Exactly.
He's
been asking. He's been asking better questions than me.
Oh, no.
Maybe. Okay. We'll get back on track here. I'll keep you here for now. Adam, you're a fantastic guest. And I do want to hear more about your journey into science. You said you kind of talked about that there might be some other personal stories, and we love hearing about. That's our goal here, is to humanize the scientist and get to know each of us as people. We're not just these robots that do science. So I'd love to hear more about your journey and how you got here.
Yeah, absolutely. Let's see. Well, I'm a bit of a black sheep in my family because everyone else in the immediate family are in the arts of some form.
Wonderful.
So I actually have a twin brother, not identical. We would joke when we were kids that we were nocturnal, but I don't think a lot of people put that we were just sort of replacing fraternal with nocturnal. It's a silly joke. But so he's a screenwriter, and so went to film school down in LA at USC, and is a comedy screenwriter. And so everybody's always like, he must be funnier than you. Yeah. Which he is. And then my older brother, 2 years older, is a cellist. And then my father is a symphony conductor, classical music. And my mother is a musicologist, which is sort of a cross of music theory and music history. So she actually writes program notes for symphonies all over the world. When you go to a classical music concert, you read about the composer, read about the soloists and the symphony, and she writes a ton of those. And so she gets to delve both into like all the complex melodies and harmonies and all the actual theory behind the music, but also just all the history. So I think that's pretty neat.
That is pretty neat.
So what happened to you?
Yeah, I know, right? Yeah, how'd we get this nerd? Yeah. So okay, I think first of all though, I give huge credit to both my parents. So my dad was a joint math and music major and recognized all of the, complex, really important connections between math and music. And so like I have all these really great memories of sitting on his lap when I was a kid and getting tickled if I got my multiplication tables wrong. So he really recognized the importance of both of those. But also my mom, I mean, she is the most supportive and most sort of, what's the right word? Like she would do so much with us as kids of all types of activities, whether it's, really great arts and crafts or taking us out to go on wonderful hikes, but also doing science experiments with us, like crystallizing crystals on the insides of eggshells or, using the kind of purple water that you get out of purple cabbage when you boil it as a pH and as an indicator of acidity or basicity. So she did so much of that with us. And I think I really credit that a lot with just helping to really encourage what I think was already there as my love of like science and the natural world. But then also both of my grandfathers, so maybe it skipped a generation, were in the chemical sciences. So I really enjoyed always talking with my mom's dad. He was a chemist and worked in the rubber industry and was kind of more of an organic chemist, so dealing with a lot of carbon and hydrogen. But then also my grandfather on my dad's side, he was a chemical engineer working on catalytic converters for Standard Oil, which later became Chevron. And so he had something like over 50 patents and really did a lot to improve the efficiency of catalytic converters. But I think that one of the things that I appreciated most about what he was always doing is he had this very unique brain where he would sort of come up with good ways to be more efficient or use the like $5 hardware store solution instead of the like really complicated fancy equipment. He'd bring like a coffee grinder in to grind up his catalysts instead of, like some really expensive instrument from a company. And so his brain was always working at like the sort of outside the box, interesting ways to get at a problem. And so I really appreciated all of that. But of course, got to talk a lot of science with both of them and do science experiments with them too.
Wow. So lots of science and art in your background.
Yeah.
Do you do any kind of art? Are you a musician yourself?
Growing up, my brothers and I were all encouraged to both learn to play the piano and to read music, but then also choose an instrument of our choice. And that's how my older brother got into being a cellist. But my parents were so great about it. They like sat him down and were like, hey, it's really hard in the arts to like support yourself and we don't want to push you into anything, but he just really loved it and he's doing great. So,
Wonderful.
But,
what was your instrument?
So I played oboe.
I played oboe.
No way.
Yeah.
Cool.
I've not met another oboe player.
Yeah.
Ever really. Yeah.
We are few and far between.
Yes.
I sadly don't play anymore.
Me neither.
Yeah. I mean, so I think for folks who don't know it, like there's so much upkeep related to an oboe. Both, it takes really strong mouth muscles to form your mouth around the mouthpiece, but also once you get to a certain level, people kind of expect you to carve your own reeds that you use on an oboe, and that's kind of a lot of work. So yeah. But what it did help with is, so you can't march in with a double reed instrument. So that's like oboes, bassoons, English horns, because it's just like it'll mess up how your mouth forms around the instrument. And so typically marching band is like a requirement in band in high school, right? But so I was in band, but I didn't have to march. And so I got the extra free time. I even got to go with the band to Hawaii, but like they were off marching while I was chilling on the beach. So it was pretty fun.
That's fantastic.
I have.
Did you have a similar experience?
My school didn't have marching band. We just had regular band. But we had 3 oboes, which is kind of unusual to have that many oboes in a band. And my cousin was actually the other one of the oboe players. And by my senior year, I was kind of over it, but I didn't want to go to study hall because I liked hanging out with my band people.
Sure, yeah.
So I just pretended to play because I had to pay for my own reeds. My parents wouldn't pay for them, and one of mine broke. And I was like, I'm just going to pretend I could squeak out like a few notes whenever I needed to, and then I would just hang with my best friend who was a trombone player. And then I really haven't. I regret not sticking with it. I wish I could still like pick it up and play, which maybe I could a few notes, but. I kind of was using it for ulterior motives by the end. I took lessons for like 6-7 years, I think. But
wow,
that's pretty funny.
Yeah, I was like, my cousin's got this. She like went on to play in college and stuff. She was excellent and more motivated than I was.
Well,
I did not care.
You guys are gluttons for punishment. This is
one of the do you play anything?
What doesn't you play?
Well, I struggle to read music. My dad insisted that I learn music the proper way because he always played by ear, and he was pretty good. He plays piano by ear. He played in church growing up, and he really insisted that we all learn how to read music, which I reluctantly did. I was terrible at the piano. Then I found the upright bass when I was in high school, and that was a lot of fun. I like to play string instruments, so upright bass, guitar, and whatever string instrument I can get my hands on.
Oh, very fun. I kind of regret not doing either like a string instrument or something else that you can kind of more like jam on. Yeah. Like nobody's sitting down and jamming on an oboe. Like,
no, they are not.
I've not heard of any jazz oboists or anything like that. Yeah.
No.
Well, I see an opportunity here. Maybe like a dual jazz
for some other
oboe.
Wonderful oboe players.
Yes.
Maybe not the ones in this
two
room.
of them right here. So.
No, I actually think I took my son to get his instrument for band a couple years ago, and it was like you could try all the instruments, and I did try the oboe. They're like, you can try it, and so I tried to squeak out a few notes a few years ago. I was like, I have lost all mouth muscle, all breath control, so I think it's no longer in my future. But I also played piano, so I do still play the piano now and then, but not as often as I'd like. But it seems like most scientists do have some type of artistic hobby practice, and even beyond a hobby, there's a lot of accomplished artists who are also scientists. And it's interesting that you do come from such an artistic family, with also a line of scientists. So, I mean, obviously you don't play oboe anymore, but do you do anything else?
Oh, right. That was the original question.
Yeah. I forgot you asked.
Yeah, let's see. Well, I maybe this is entirely unsurprising as a chemist that I also like to cook. So even though, we got to do that to eat and all that, I do enjoy it and try to sometimes at least have fun little cooking projects. Recently learned about velveting meat to make it a little more tender. So this is a lot of like restaurants, especially that do like stir fries, do this, where you, especially if you slice the meat really finely, you kind of coat it or soak it with some baking soda for a little while and then wash that off. But chemically, that's like tenderizing the meat. You wash off all the baking soda so it doesn't taste bitter or anything like that. But that's why, if you go to a restaurant and like your mouth really bites through the meat cleanly and really easily, that's often like velveting is apparently.
I'm going to have to try that.
I didn't know that.
Awesome.
Especially, I've struggled to make Asian food. I really, which is a broad category, obviously, but there's just something that they're able to do that I'm like, I don't know, but that might be one of the things.
Might be, yeah.
I'm an expert at eating all forms of Asian food, but that's like one whole continent of food
true.
That I cannot cook. But.
Well, maybe let me know if you have any good restaurant recommendations in the area. I'm always on the lookout. I've been here, 4-ish years, 4.5, but always looking for more.
There's a couple places here.
Okay.
Yeah.
Okay.
Yeah, we just had Asian food for lunch before this.
Too bad.
Yeah. Like we go to, I don't know, Num Num Pho is our favorite.
Yeah, that's a good
one of our favorite local Asian
It's good for
restaurants.
like a quick.
I would say that I actually think it has the best ramen in the area that I've had so far.
That's what I had today. It's the first time I had the ramen. It was really good.
Okay. Yeah, ramen is great.
This is such a scientific conversation.
Yeah. And then let's see. I also, try to stay healthy, do some running and play soccer. And what else? Yeah, I think in terms of other creative outlets, mostly just, every now and then, pick up a jigsaw puzzle or my partners especially loves those. So that can be fun. And during the pandemic, certainly did some paint by numbers. I've one or two of those hanging around. And,
very nice.
Yeah. That's about it in terms of the creative stuff. Yeah.
Well, we love soccer here on Rust Belt Science. So tell us about your experience with soccer.
Well, I want to know your favorite team as well. We've had a few people who refuse to say. And
oh, boy.
It's okay if you don't want to.
Or player.
I can almost do it by eras because I'm no longer as like closely following soccer, like professional soccer, watching it, and always just enjoy a good game. But back in the day when I was much younger, I adored watching Los Galacticos, like Real Madrid, when it was like Figo and Ronaldo, like the Ronaldo, Brazilian Ronaldo, and Zidane. Zidane was always my favorite. But at various other points, I've enjoyed watching a lot of the English Premier League and even, where I grew up in California, there's a very large Mexican population. And I really also got into like some of the Mexican teams too. Where I'm from, Stockton, California, sort of at least for a while set up kind of like a sister city thing with Guadalajara, which is where Chivas is. And so Chivas would come and play in Stockton a couple times a year. So that was pretty fun to go to those games. So it's just kind of gone by eras. And from a national team standpoint, it was always fun watching Brazil, but then for a while Netherlands and then Germany, and always hoping the U.S. could do better.
Well, my team is borderline about to get relegated, so
I think they'll make it.
Barely.
What's the team?
I'm a Tottenham fan.
Oh, okay.
So they're not doing great, but
they're not at the bottom of
they're close. They're getting there, and everyone reminds me of it every day.
I think their only saving grace this season, and we're recording this in April, so there's 5 more games.
Yeah.
I think that their saving grace is that the 3 bottom teams just have lost worse.
Well,
that's
I
about
appreciate
it.
The vote of confidence.
That was me trying to encourage you.
Yeah.
Well, Adam, I just want to say that this has been such a wonderful conversation with
you.
And if you
same for me. Yeah. Well, thanks so much for chatting with me.
Yeah, of course. And if you want to leave our lovely listeners with just one thing, either about your work or about chemistry in general or about material science or the world or soccer or cooking.
So many things.
You're really leaving it open-ended for him to say what
it is open-ended, and we'd love to hear it.
Let's see. I think from the scientific standpoint, I would just say that, there are all of these like very fundamental concepts that eventually will end up translating to really important developments. And to not forget that there is so much value, as we've been talking about, in fundamental research, and just the idea that we know a lot of the things that are needed to meet demands in whether it's medicine or energy or anything in between, all of the challenges facing humanity. And so you can extrapolate back from that and know, okay, well, here are a lot of the criteria I need to hit. And so here are the right areas to look. But where we then need to look there and come in with sort of an open mind and really to fundamentally understand as much as we can so that we can then move down that spectrum all the way towards like the eventual application. But then, also from a just sort of intellectual curiosity standpoint, I truly, truly enjoy doing all of the science that I get to do with my students and getting to talk about it, and to teaching. So I truly enjoy like teaching and talking about science. And so, I just try to hopefully bring a little bit of the color of chemistry to the world and have it not be quite such a dry topic. And so hopefully that comes through.
And you do communicate science very well. And in fact, this is something that you're really interested in, the science communication.
Yeah.
And you mentioned earlier in an early conversation that we had that you and your lab has started a YouTube channel
This is right.
To tell us a little bit about that, and then take your time.
This honestly, maybe this was inspired by my dad's dad. Those $5 hardware store solutions for the kind of expensive problems, coupled to, I think there are problems in inaccessibility in science where there's a lot of this accumulated practical knowledge, very like esoteric knowledge, stuff that you wouldn't get unless you were working in a very specific lab for kind of a long time and then eventually hear about it. Like, it's not even talked about always in the supporting information that gets published with every paper, which, by the way, those supporting informations are more often than not available to the general public, and you don't have to get, past the paywall of a journal to see it. Yeah. And so, but even in those supporting informations, you can't convey exactly how some technique was done. And so there are all these issues in accessibility in science, both cost, but also these knowledge barriers. And so my goal with this, what we call Lab Hacks, that's the name of the YouTube channel. I think it's at Lab Hacks, if you search it. And first of all, let me just say I am by no means good at like any form of social media whatsoever. And this is in its kind of infancy, its starting stages. So we have probably a little bit of an embarrassing number of followers and all that. But we're starting to put it out there. And really the goal is to have this repository of really quick, digestible, easily understood videos filmed in both English and Spanish that teach either, here is this like really cheap solution to something that you would normally have to pay, like some famous like scientific supply companies like that maybe I won't name, but pay them a lot more money to get the same thing. And so this could be anything from sealing a bit of paperclip in glass with just like a blowtorch, and there's a chemically resistant stir bar that you could sort of then throw away when you're done with it and not have to worry about like a really expensive scientific stir bar coated in Teflon or something like that. Yeah. Or using a cheese slicer to cut a piece of soft like sodium metal that you're using in your inert atmosphere glove box. Or, just using a cactus spine to pick out little crystals that you're going to measure on a scientific instrument instead of some like expensive metal probe that you might typically use. So really just, coming up with like those tricks of the trade that are so prevalent in all forms. And I would love if either of you, I'm sure everybody's got these little tricks of the trade, right, in their own respective fields. Yeah. So we're trying to film lots of those in really kind of quick videos and get them out there and just try to like help folks with doing science and also doing eventually, hopefully, more science demonstrations that especially younger scientists, budding scientists can do at home. Maybe even some of those like, cabbage pH water experiments or eggshell crystallizations that I was talking about earlier.
Well, that's wonderful. And I really love the fact that you have these videos in both English and Spanish because that really expands kind of the audience base.
Yeah. That was our goal. And I actually have if we should start dubbing it in even more languages, my group, I think we could do Chinese, Sri Lankan, German, Sinhalese. That's Sri Lankan. One of the many Sri Lankan languages. Yeah. We could probably even do some other ones. So that'd be the goal eventually.
There you go. Yeah. And that's actually a really good point that you make because science is such an international endeavor. Right. And I've met most of my international friends. We all have met most of our international friends working in labs and in different labs. And that's such a great way to kind of combine our powers in a way.
Absolutely. Absolutely.
So at Lab Hacks, so our lovely listener, check it out. And
I'm going to check it out even though I'm not an organic chemist, but maybe there's something for me.
Who knows? Maybe you're going to get the Rust Belt science bump, I guess.
That'd be neat.
All 5 people who are listening to this show.
It'll keep us honest and make sure we're continuing to put more of those videos out too.
That's wonderful.
Well, I'm going to check it out. I'm going to share it. I'm not very good at social media, but I think it's a really, I'll use the word beautiful. I think it's beautiful. This is what scientists do. They share, and that's what makes science so cool, is it's super collaborative, and it can get nasty sometimes, but generous scientists are just absolute gems to share knowledge and tips and resources and make it accessible for other people to come in and join the group.
Absolutely. It is a collaborative effort, and I will share it with like all of my 35 followers on whatever social media.
Well, thanks.
Yeah, exactly. Including my mom, I think.
Yeah.
Oh my gosh.
God love moms doing cabbage and listening to the podcast.
That's great. I got to tell you, that cabbage experiment, it really carried us through about half of the pandemic with my kids.
Oh, that's great. Yeah.
A lot of fun. We got all the cleaning solutions to see what color they're going to change that thing, and then, lime juice and everything changed that cabbage a different color. So it was really, really cool.
That's fun times. Can get a little stinky, but now apparently you can also buy there's a flour called a butterfly pea, PEA, flour powder, and you can just buy that, and that does the exact same thing.
Oh, really?
So,
yeah.
Also makes fun purple drinks. But,
I have some at home. I'll have to pull it out and try it.
Oh, there you go.
Yeah.
All right. Awesome.
All right, Adam. I feel like we could talk for a lot longer, but we will give you back your time so you can keep doing awesome science and enjoy. It's Friday, so enjoy the rest of your Friday as well. And hopefully we can have you back on and keep talking about all these cool things and science communication and getting stuff out there into the community. So thank you so much for your time, Adam.
Thank you both so much. It's been a real pleasure chatting with you, and just thanks for having me on. And thanks for doing what you're doing. I think this communication about just sort of humanizing, but also bringing science to as many people as possible is a wonderful, wonderful endeavor.
Thank you. Appreciate it. All right. Until next time.
At the end of our show, we would like to thank you, our lovely listener, and our awesome audience for spending your time with us. We thank the Notre Dame College of Science and the Indiana University South Bend College of Arts and Sciences. Special thanks to the wonderful people at the Notre Dame Studios. Coming to you from beautiful South Bend, Indiana, in the heart of the Rust Belt, this is Rust Belt Science. I'm Shahir Rizk.
And I'm Maggie Fink.
And we'll catch you next time.